Let's clear something up right away. A black hole is not an empty void in space. When a massive star reaches the end of its life, it collapses inward until its entire mass is compressed into a single microscopic core. You are looking at a huge amount of matter packed into a shockingly small space. Over a century ago, Albert Einstein's theory of general relativity predicted exactly this outcome. His math showed that if a star's core is dense enough, gravity overwhelms all other physical forces in the universe. The pull becomes so intense that nothing can move fast enough to escape it, not even light itself. Because our eyes rely on light reflecting off objects to see them, this creates a frustrating problem for astronomers. You cannot directly look at something that traps all light. But extreme gravity provides its own workaround. A black hole bends the very fabric of space around it, acting like a massive, invisible magnifying glass. This bending gives us a way to observe the unobservable. Imagine a star located directly behind a black hole. Normally, that star would be completely blocked from our view. But because the black hole warps space, the light rays emitted by that background star actually curve around the dark sphere and continue straight toward our telescopes. Some of these light particles, or photons, get caught right on the edge. They orbit the black hole 2, 3, or even more times before finally shooting off toward Earth. This creates a bright wing of light, meaning you are literally seeing the backside of the black hole pulled into your field of view. In 2019, an international team of scientists used a global network of telescopes to capture exactly this. They released an image showing this glowing photon ring surrounding a perfectly dark center. But that glowing ring is just the waiting room. To understand what is actually happening on the inside, you have to cross the ultimate boundary in physics. That boundary is called the event horizon. It marks the precise distance from the center, where the gravitational pull requires an escape velocity faster than the speed of light. Since nothing can travel faster than light, this is the literal point of no return. Once you cross this line, the laws of physics invert. Space and time swap their mathematical roles. Moving toward the center becomes as inevitable as moving forward in time. You can no more turn around and fly out than you can travel back to yesterday. If a friend were watching you fall from a safe distance, they would never actually see you cross the horizon. From their perspective, the light reflecting off you would stretch. You would appear to slow down, freeze in place, and gradually fade to red until you completely vanished. For you, the descent is much more physical. If you fall feet first into a typical stellar mass black hole, the gravity acting on your feet is drastically stronger than the pull on your head. This difference in force stretches your body vertically while compressing you horizontally. Physicists call this process spaghettification, and it will rip you into a string of individual atoms. If you want to survive the crossing, you need a supermassive black hole, one millions of times heavier than our sun. Their event horizons are so wide that the gravitational pull on your head and feet is practically identical as you cross, keeping you perfectly intact, at least for a little while. Deep inside, past the event horizon, lies the singularity. This is the theoretical center where all the matter consumed by the black hole is compressed into an infinitely small point. Here, gravity and density become infinite, and every law of physics we know breaks down. Mathematical models suggest this singularity might not be a dead end. Instead, it could form an Einstein-Rosen bridge, often called a wormhole. This acts as a tunnel stretching through the fabric of space-time, connecting the black hole to a completely different location, or even a different era. At the other end of this tunnel lies a hypothetical object called a white hole. While a black hole sucks everything in, a white hole violently expels matter and energy outward, acting as the exit door for our cosmic subway. But don't pack your bags just yet. These theoretical bridges are incredibly unstable. Even if a tunnel did form, the crushing density and lethal radiation inside would destroy any physical object attempting to travel through it before it ever reached the exit. Because surviving the physical journey is mathematically impossible, we can't rely on classical physics to tell us what happens to the stuff that falls in. To answer what is truly on the other side, we have to shrink our perspective down to the quantum level. In quantum mechanics, there is a strict rule: information can never be destroyed. The specific arrangement and state of the particles that make up you, a planet, or a diamond must always exist in some form, somewhere in the universe. This creates a massive problem for physicists. If a black hole acts like a cosmic trash compactor, squeezing everything down into an infinitely dense, chaotic point, what happens to the quantum information of the objects it consumes? This is known as the black hole information paradox. The late theoretical physicist Stephen Hawking dedicated much of his career to solving this exact contradiction. He discovered that the edge of a black hole is not completely quiet. Thanks to quantum fluctuations, pairs of particles spontaneously form right at the event horizon. One particle falls in, but the other escapes. Over trillions of years, this escaping Hawking radiation drains energy from the black hole until it evaporates completely. But Hawking proposed that the original information swallowed by the void isn't lost when it evaporates. Instead, he theorized that the black hole might funnel this data into separate baby universes that branch off from our own, containing different realities that we can never observe. There is an even stranger solution to the paradox, known as the holographic principle. This theory suggests that the inside of a black hole isn't a three-dimensional space at all. Instead, all the complex three-dimensional information of everything that ever crossed the boundary gets perfectly encoded on the flat, two-dimensional surface of the event horizon. It acts like a hard drive storing the data of every swallowed star and planet on its outer shell. If the inner depths of a black hole are truly just a two-dimensional projection, it forces physicists to ask a dizzying question: could our entire universe operate the exact same way? These gravitational monsters consume stars, planets, and even our classical understanding of reality, standing as the absolute limit of human comprehension. Quantum mechanics dictates that fundamental information about a particle's state can never be destroyed, but a black hole crushes everything into an unreadable singularity. To resolve this, some physicists argue that the consumed data is hidden safely away inside a newly branched, self-contained baby universe that we just can't access. There is a competing, far stranger solution: the holographic principle. This principle dictates that the information never actually falls into the singularity at all. Instead, the data of every consumed star, planet, or astronaut is encoded mathematically and left resting on the two-dimensional surface of the event horizon. If that math holds up, the other side of a black hole might not be a physical destination. It could be the ultimate proof that our entire three-dimensional reality is merely a holographic projection of two-dimensional data.